Sorry. Welcome everyone to this talk titled Kongloader, which is about the hidden art of rolling shellcode decryption, especially relevant to offensive security engineers that are, let's say, red teamers, which want to load shellcode on a daily basis or during their red team operations into the memory of a computer of a victim that clicked malware while remaining undetected. But it's also relevant for defensive security engineers. So let's say that you're a SOC analyst and you want to know more about how shellcode loading works, but also maybe know more about the techniques of shellcode loading that you might encounter in the near future and how to detect them. This is a talk for you. It's research that I started a while ago, and it's actually not yet finished, I have to admit. It's about halfway done, yet the results are already really promising, and I hope today that I can inspire you with these results so that you can use them in your daily job and apply them yourself. But before we dive into that, let me briefly introduce myself. My name is Tijme Gommers, like I was just introduced. I work at ABN AMRO Bank as an offensive cybersecurity engineer, and most of the research that I put into Kongloader, I did at ABN AMRO Bank. And besides that, I also do digital forensics at Hunted, which is a Dutch national television show. So if you're from the Netherlands, you might sometimes see me hacking in a corner on television. And before that, I had a career in red teaming operations. So I had hands-on red teaming experience for about 6 or 7 years. And this is also where I built some of my exploits and my malware that I published on my GitHub profile, but also where I got the idea and where I often needed to load shellcode while remaining undetected. So if you want to ask me anything about this presentation afterwards, feel free to reach out to me on my social media. My username is my first name, so that's really easy. And I'll be around for the entire 2 days, so you can connect with me. And also the project, I'll publish it on GitHub, in 1 month. And I'll also publish some parts right after this presentation. So, like I said, this research started a while ago. I was chatting with an old colleague of mine, Michael, and I told him, you know what? I was busy with a red teaming engagement. You know what? We should build a rolling shellcode decryptor. Something to stay under the radar again. And he told me, well, I'm not sure if that would work in practice, Tijme. Yet about half an hour later, he came back to me and said me, well, seems like it does. I built a proof of concept. And he even sent me a nudge afterwards. And this is the proof of concept that he built. He defined an encryption key, a XOR encryption key. He then defined shellcode, 2 instructions that were encrypted, a move instruction and a return instruction. He defined this proof of concept function, and later on he defined this main function which called that proof of concept and printed the result. And although the shellcode was encrypted, this worked, and he could print the result in plain text. And I thought this was awesome, because this meant that the shellcode was never in plain text in memory. So I decided I should extend this beyond these 2 instructions. I wanted to support entire shellcodes of C2 frameworks, like Cobalt Strike, for example. But before we dive into how that works, let's briefly align on how shellcode and shellcode loading works. I'm sure many of you are familiar with it, but some of you might not yet. And there are 2 types of shellcodes, namely position-dependent code, that we see on the left, and position-independent code. And position-dependent code is what we all know when we program malware or some kind of shellcode. Let's say we want to print a message, hello. We just define the message and we call printf and it would print hello. And if we compile this to assembly, it would look more like this. We've got a data segment, which contains the hello string, and we've got a text segment, which contains the actual assembly instructions that will be executed. Now the problem is that whenever you want to load this shellcode into another process, inject it, the shellcode only consists of the assembly instructions and not the other segments in the PE file. So you would extract only the text segment and inject it into another process, but it would reference the data segment. And thus the program would crash, because it references invalid memory, or it would print some gibberish. And to fix that, you want to write position-independent code. which looks more like what we see on the right. It looks kind of similar, and when you compile this without any compiler optimizations, you get assembly code that looks like this. So we see that the data segment is gone, and now only we have the text segment. And you can see that the hello string is now allocated inside the actual instructions that will be located on the stack. Which means that if you extract the text segment, which is essentially the shellcode, you can inject it anywhere in another process and it will just work and it will print the hello message. Now this seems to be really easy to program like this for printing an hello message, but if you want to write an entire C2 beacon, obviously it becomes much more difficult and there's a lot of overhead, so you don't really want to program position-independent code directly. And as red teamers, we found a solution that you can already use to date, which is reflective loading, something like the Wover's donut. I'm not sure if you are familiar with this, but it's a tool that you can use to input any position-dependent code, so an executable, and it will output, position-dependent code, it will output position-independent code. Now there's usually some confusion about the Wover's donut. People think it actually converts your code. It does not convert your code from position-dependent to independent. It actually wraps around your position-dependent code with a position-independent wrapper. Meaning that, of course, the advantage is that it's really easy to use, but the disadvantage is that your shellcode becomes really, really large. And this is often not what you want when you perform red teaming engagements, because you want to have as small shellcode as possible so you can wrap it into any kind of loader that you can ship to a victim. But no matter how you get to your shellcode, you eventually want to load it. And this is how that looks like in the most simple way. So you define your shellcode on top in an array, a byte array. You then allocate a read-write-execute memory segment, which is highly OPSEC unsafe, but it's the easiest way to accomplish shellcode loading. You then copy the shellcode into that memory segment and you execute it, and it prints the hello message. Easy as that. The problem is that if your shellcode does something malicious, so let's say it's a C2 beacon, then it will be detected, because there is, on execution of it, an initial memory scan by EDR or antivirus on your computer. And EDR will trigger on this execution, scan the memory segment, and it will find out that there's a cobalt strike beacon in there, and it will trigger an alert. So as a red teamer, you are then detected. And even if that's not the case, then there will be behavioral analysis. So let's say you embedded a C2 beacon, then the C2 beacon does something malicious because you typed in a command to do something. Then behavioral analysis will trigger in the EDR, and the EDR will scan the memory segment, and you will be detected again. And even if that's not the case, there are continuous scans. So let's say every hour EDR scans your memory, and you can be detected as well. Now we've thought of something to resolve this issue, and it's called a sleep mask. Who has ever used a sleep mask before in red teaming engagements? A few people. So how does a sleep mask work? Let's say you have your loader, and it can be anything. It can be an executable that you send via a phishing mail, but it can also be an Excel macro or something else. You have your loader, and in the loader, your shellcode is embedded in an encrypted way with something like a XOR key. Then on execution, when the victim executes your malware, the loader decrypts your entire shellcode in memory, and it will then execute it. And if it's a C2 beacon, it will connect to the C2 server, get some commands, and run them. And it will then afterwards encrypt itself again, and it will sleep for a while. So usually you see that there's a sleep of 30 seconds between commands, so that there's not much network traffic generated. So you cannot be detected network traffic-wise. And after those 30 seconds, the shellcode decrypts itself again, executes a new command, and encrypts itself again, and so forth. Now this is lovely because there's a lot of time in memory where the shellcode is encrypted and is thus not detected. But there's also a time where the shellcode is decrypted in memory and can be detected. And this is especially the case if your shellcode is not multi-threaded. So let's say you run a command in your C2 framework that takes quite a while. Let's say you run sharphound, which you shouldn't do for OPSEC purposes, but let's say you do. It runs for quite a while, and that means that your beacon is decrypted in memory for a very long time. And this is exactly the issue that I tried to fix with Kongloader. So let's briefly take a look at the concept of rolling decryption that fixes this issue. We have a similar slide as before with a loader. That can be your Excel macro or an executable. And it has your shellcode embedded in an encrypted way again. Now, instead of decrypting the entire shellcode on execution, instead we decrypt just one instruction. Only the first instruction. We then try to execute that instruction, and we then encrypt it again. And we do that again. We just move to the next instruction without sleeping. So we decrypt it, we run it, and we encrypt it again. And for the next one as well, decrypt, run, encrypt. And so forth. And this means that only one instruction is visible in memory at the same time, meaning you cannot signature the beacon in memory. But it's quite complicated to get this to work, technically, in actual production code. There are a few possibilities to do it, and one of them is with vectored exception handling, and that's the version that I tried to build. And I'll show you an example of how that works. So here we see the shellcode loading that we initially saw in a few slides back. We defined the shellcode on top, we create the read-write-execute memory segment, we copy the shellcode to it, and then we execute it. Now we convert it a bit, and we add three things to it. First of all, we add a vectored exception handler, which is basically a function, which we can see in the second argument, called exception handler, a function that is being called when an exception occurs. Afterwards, we set a breakpoint on the initial address of the shellcode. And this breakpoint is basically an exception in C, so it will trigger the exception handler on the execution of the first instruction. And the exception handler itself can be implemented as well. And it looks like this. We just decrypt the current instruction, and then we continue execution. And that should work, and it should slowly, gradually decrypt our shellcode and run it. Now this is pseudocode, obviously. If you look at the actual C code behind it, it looks more like this. So let's say for set breakpoint, I used hardware breakpoints. So there's a function in the Windows API called getThread context, in which you, basically get the context of the current thread. We see that here called LP context, and it has some attributes that we can use called debug registers. So DR0 till DR7. And in DR0, we can set a specific memory address that we want to breakpoint on. And in our case, that's the first instruction of our shellcode. And in debug register 7, we can either put it on 1 to enable the breakpoint, or we can put it on 0 to disable the breakpoint. So in this case, we set a breakpoint on the first instruction of the shellcode. And then for the exception handler, it's a bit more extensive. What it does is, at first, it looks at if there was already an instruction that has been decrypted in the past, and if so, it tries to encrypt it again. Afterwards, it tries to decrypt the current instruction that should be run, which is at maximum 16 bytes, which can be signatured, but it's not really possible to signature on that. And afterwards, we calculate the next address that we should breakpoint on, and we set the new breakpoint. So it's the second address, and the third address, and the fourth address, and so forth. And we use exception continue execution to ignore the exception, basically, and just continue the execution. And that's how we fix the rolling shellcode decryption, execution, and encryption with Kongloader. So I built this, and I was pretty proud of it, and I told it to my colleagues, of course, that we should use it in red teaming engagements. But then a few weeks afterwards, a colleague of mine sent me a text message on WhatsApp, and this was it. It's in Dutch, so I'll translate it for you. He told me, "Wasn't this what you were also busy with last time we spoke?" And he sent a GitHub project called VoidGate. And apparently, as always, someone 4 months ago built the exact same thing. If you ever encounter this, don't feel down, just continue your research and publish it, because there might be differences in the research, and it turned out to be as well for Kongloader and VoidGate. And although VoidGate is an awesome project, it has some downsides as well, especially that it's quite slow in execution of shellcode. And that is because instead of calculating which address to breakpoint on, they use a trap flag approach. So a trap flag is something in your CPU which you can set in the eflex part of your context, of your thread context, and it will define that you need to breakpoint on every single instruction, even outside your shellcode. So you can imagine that takes a while if you use a lot of Windows API functionality. And there are some more caveats and enhancements that can be made, both to VoidGate and to Kongloader, and I'll go through some of them. Going back first at the endless execution, the slowness of VoidGate, and how to resolve that in Kongloader. So to give you an example, a simple hello world shellcode would take 13 million breakpoints in VoidGate to properly execute. In Kongloader it only takes 2000 breakpoints, so it's much faster. And if you look at a simple stage beacon, well, for both of the projects it takes millions of breakpoints, and about 30 seconds to launch a simple beacon. Now if you look at the stageless beacon, which doesn't connect to an HTTP server to receive the full beacon, you're looking at even more breakpoints and a longer execution, and it didn't even try this yet. Now why is this the case? Let me visualize it a bit. What we see on the left is how VoidGate uses breakpoints to simulate the rolling decryption. We can see that we set an integer, we define a string, and afterwards we call a Windows API, shell execute W. And we can see that even in the Windows API, VoidGate tries to breakpoint on every single instruction. Now how can you fix this? Obviously, when you see a call to a Windows API, you need to bypass it somehow. And I used Zydis for this, which is a tiny disassembler that I embedded in Kongloader. And with Zydis, in the exception handler, I can check what kind of instructions are to be executed. And if it's a call instruction or a jump to a certain address, I check whether that address is within my shellcode or not. If it's within my shellcode, I just set the breakpoint. But if it's outside my shellcode, I calculate where the breakpoint or where the function eventually would return. And this is not always the exact next address, it can be somewhere in the shellcode. And based on that calculation, I set the breakpoint efficiently, and it would only take 4 breakpoints for the same code. Now, like I said, there are some more caveats and enhancements to be made. Because it seems easy to do this, but you can have, for example, fake encryption states when you execute certain shellcode using this technique. We've got an example of that right here, which you would encounter with MSF Venom payloads. I'm not sure if any of you have used Metasploit before, or MSF Venom to generate payloads. Maybe some. If you generate an MSF Venom payload, which is basically malware, some of the strings or data that you need to run the payload will be embedded at the end of the shellcode. So let's say you generate a WinExec payload, your CMD line will be embedded at the end of the shellcode, in this case represented as the 4 bytes at the end. Now let's say we have a loader that just wants to print the result of the 4 bytes. Then, well, first it would get the address of the 4 bytes and move it to RCX. It would then get the value of RCX and move it into EAX. And it knows how many bytes to move, because EAX has a certain size. And based on this move instruction, I intercept it with Kongloader and Zydis, I decide to decrypt the value. But in this case, if you're not doing that, you would return encrypted bytes, and it would crash the program, or you would print gibberish. So like I said, I use Zydis for this. So if I encounter a certain move instruction, I check whether the move source data is inside my shellcode, and if that's the case, I decrypt it first. And like I said, that's easy because we know the size to decrypt. But it becomes more complicated if you don't know the size. So let's say you have a shellcode that runs a Windows API. Well, then you get the address of the 4 bytes again, and then you call the Windows API, but then you send encrypted data to the Windows API, so it will crash or at least return an error as well. So how would you overcome this? Well, we can again use Zydis for it. And it looks like this. We can define certain signatures of functions, of Windows APIs, or you could use the Windows debug symbols for this, because they contain the same data. And let's say we encounter a shell execute, function, then we know that the argument to this function, well, is cmd.exe/something/calculator, for example. And we know that that string is null terminated. So what we can do is we can decrypt each byte at that pointer until we encounter a null terminator, and then we just stop. Now it becomes more difficult when there isn't, when it isn't a string and there's no null terminator. So what you could do then is look at the signature of the function again, and usually the size of the data is passed as an argument. So based on the arguments in the registers, we can determine the size and decrypt the data to be passed to the Windows API based on that. And that's what I did with Kongloader as well. Now there's one more thing that was a problem for me, and that was fake execution states. So let's say you run shellcode with Kongloader that is multi-threaded. Well, the breakpoint technique that I used only works on one thread. So let's say the shellcode runs create thread. What happens then is that Kongloader loses control of the encryption and decryption. So thread 1 of your shellcode would decrypt an instruction, or Kongloader would do it for it. Then Kongloader would, for thread 2, maybe encrypt that same instruction in the same shellcode, and then thread 1 decides to execute the instruction, but it's already encrypted, so it would crash the program. Now there's a simple solution to this. We can use Zydis again, and on create thread, we can ensure to duplicate the shellcode with the current encryption state in memory. So we have two instances of the shellcode in memory, and we point the newly created thread to the second instance of the shellcode. And then we resume both threads. And that means both threads can decrypt and encrypt instructions at the same time. And it will work unless the create thread was called with some arguments pointing to the initial shellcode. But I haven't really encountered that yet in any production shellcode, luckily. Now you would say that using all this Zydis and instruction interpretation, the code becomes much slower again, the Kongloader technique. And that is actually kind of true. And as well, if we interpret all these instructions, aren't we just building an interpreter, right? And instead of vectored exception handling, shouldn't we maybe call it fake, endless, and horrible malware? I would vote for no, because there's a solution to this, and I'll get to it at the end of the presentation. But let's first take a look at some of the caveats for defenders, because it's quite difficult to detect this technique. Let's say you are a SOC analyst and you want to run this malware or analyze it somehow, and this malware uses Kongloader to execute. You would probably run it in an isolated sandbox. However, usually these isolated sandboxes are quite slow. Let's say you use AnyRun, for example. And because of all the exceptions that occur, the sandboxes aren't really capable of executing the malware properly. And besides that, due to all the executions, it's also difficult to do behavioral analysis that way. So instead of using a sandbox, you would likely better maybe use a debugger for it. So let's say you use WinDBG to debug the code. I tried it because I needed to develop this program, and I encountered some issues, so I ran it in WinDBG myself, but it doesn't work. Because there are millions of breakpoints happening in the code, because every instruction is one breakpoint. Which means that in WinDBG, you need to click continue 1 million times. Well, that's not feasible. Of course, you can automate this and you can ignore the exception, but that's not really feasible as well, because if you ignore the exception, the decryption and encryption stops working. So your code will just crash. Now there's a solution to this, and it's a command, and I don't even know what it stands for, SXISSE, and it will ensure that the WinDBG will continue the execution, but the actual vectored exception handler of mine will be called in Kongloader. However, this is an issue as well, because WinDBG will then run some code on its own for each instruction, which will make it even slower. So it will exponentially become slower. So it's quite difficult to detect if the shellcode is malicious or not. Also, because EDR doesn't pick up on it yet. So if you use KongLoader and you use some EDR solution like Microsoft Defender for Endpoint, which I tested it on, it's not detected yet. You could say you could detect KongLoader's native code, so not really the shellcode, but KongLoader itself. But then you don't really know if the shellcode itself within KongLoader is malicious or not. So you're detecting it always, even though it's legitimate. Now obviously you could write a Java rule for this to detect KongLoader's native code, and it would look something like this. So you check if there's an add vectored exception handler call, you would check if CIDES is included, and you would check if there is a page read write execute being created. And that would work unless we as attackers use a polymorphic engine upon compilation of KongLoader. And what a polymorphic engine is it makes sure that on compilation the output is different every time. So certain assembly instructions are switched a bit so that it cannot be easily signatured. Now, like I said, there's some way to make this a production-ready shellcode loader, but it's future work. And what we need to do is we need to move all the functionality in KongLoader from runtime on execution to compile time. So we need to, on compile time, transpile the shellcode into something more enriched and interpretable. Let's say enriched with the size of the instructions, but also the next address that should be breakpointed on. And then we refactor KongLoader and we can remove the entire CIDES part, and it will become much, much faster again. And this is, like I said, still what to do. But you would say, aren't we just building a virtual machine then? Like VM Protect, which is a known TTP used by threat actors in the wild. And actually Fox IT, a Dutch security company, recently blogged about this. It's a really interesting blog post about how to virtualize your malware to stay under the radar. However, in its current state, KongLoader is already usable for third stage malware, which is small. And if you want to use it for obfuscation purposes, let's say in a penetration test where you get detected every time with Mimikatz or whatever, you can load it in KongLoader. Now let me give a demo of how KongLoader works in its current state. I'll give three demos actually, 2 MSF Venom payloads, and 1 Nimplant C2 payload. Nimplant C2 is a C2 framework from a colleague of mine, and for this specific project, for KongLoader, I built a truly position-independent code, which doesn't use reflective loading, so it's really tiny, specifically for Nimplant, and I'll publish that afterwards as well, so you can use it in your red teaming engagements. But let's take a look at the first demo. We generate an MSF Venom payload, win x64 debug exec, with a CMD line called calc.exe. We run it, and we have some debug output, because this is debug version of KongLoader, and we can see that the calculator instantly pops, and we can see that win exec was being called, and the size of the command line argument was guessed based on the null terminator. Now it becomes a bit more complicated when we run a reverse TCP shell, but it works as well. It takes about 30 seconds, but I've sped up the video a bit. And we can see here that we have a shell incoming and it's fully working, and there's no detection whatsoever by EDR. So I ran this on a machine with Microsoft Defender for Endpoint, while usually MSF Venom payloads like these are heavily signatured based on static analysis. They're called by emulators, they're called by dynamic analysis, they're called by the cloud sandboxes, but it just works. And then lastly, the demo of the Nimplant C2, which takes a little bit longer, but it's also an artificial delay that I quite like during red teaming engagements, because you don't always want to execute your shellcode directly, because it's more likely to get caught. But it works, and we can see a beacon incoming, and we can actually interact with it and call some commands that are present in the C2 framework of Nimplant. And again, this is fully without any detections currently. And we can see that if we run the wmi command, we are administrator. So to conclude, maybe this isn't fake, endless, and horrible malware, but maybe it is very experimental and hypothetical malware. If you want to have the Nimplant C2 beacon, you can scan this QR code. It's available now on my GitHub profile for you to use. KongLoader itself, I published it in 1 month after Black Hat Asia. So if you follow my GitHub profile, you can find it there as well. And I'll leave this QR code open for a second, so thank you.